Welcome back, everybody. In this video, what I would like to do is move a little bit beyond our general discussion of acids and bases and moving a little bit more specifically into the concept of pH and analyzing the pH scale itself. And yes, we're going to do a little bit of calculating here, so get your calculator out. Part of the challenge of the calculations certainly involves what kind of calculator you have, whether it's a Texas Instruments, which is always different than the others. Casio and Sharp and others kind of fall into a different category, so we'll get into that. Just remember that the pH scale generally ranges from 0 to 14. Yeah, we can go below 0 for a very acidic solution or above 14 for basic, but for our purposes, let's assume that 0 to 14 works. At pH 7, we know that the concentration of H plus equals the concentration of OH minus. That's true for pure water. Once we go below pH 7, in our example the other day would have been vinegar or battery acid, we know that the strength of H plus or hydronium ion goes up and the concentration of hydroxide goes down, and vice versa. Let's take a little look at the pH scale. This picture really tells the story. Remember that acidity goes up as we go below 7 and basicity goes up as we go above 7. The square bracket, very important, represents concentration, and I haven't mentioned that yet. There's nothing magical about it. It's simply the concentration of the solution in moles per liter, or C, as we have learned in chapter 9. So don't worry so much about that. In pure water, we know that the concentration of H plus is exactly the same as the concentration of OH minus. So that's interesting when you think about it. Yes, pure water kind of behaves as an acid and a base simultaneously. So that concentration, we know, is 1 times 10 to the minus 7 moles per liter. 1/10,000,000th of a mole per liter, so very small. It makes sense that the amount of H plus and OH minus are very small because it's neutral. We're going to look at this calculation in a bit. Logarithmic scales, when we look at the relationship between H plus in moles per liter plotted against pH, which we know goes from 0 to 14 roughly, it's not linear. It's logarithmic. What does that mean? Well, let's start with the solution with a pH of 7, or pure water, for example. If we were to figure out the pH of that solution, which you already know is 7, but you don't want to trust short chemists, obviously, we can figure out the mathematics of the pH by using this very famous calculation. pH is always equal to the negative log to the base 10, and we'll talk about this in a second, of the concentration of hydronium ion. When you take the negative log of 1 times 10 to the minus 7, you get 7. Now, looking at my calculator, it's a Texas Instruments. I have a log key right there underneath my second function key. That key becomes very important to me. My exponent key, which you may remember, is actually a second function, EE. The Casios and the Sharp calculators will have a log key front row center. They probably won't have an EE key, but rather an EXP key for the most part. So if we plug this calculation in and get 7 using a Texas Instruments, I have to hit my log key first. And if you see LOG on your screen, then you know that you have to hit log first. If you hit the log key first and it gives you an error, you might be using a different kind of calculator and you might have to hit the exponent key first. In any case, using my TI calculator, I press log 1 second function EE negative 7. And that will give me an answer on my screen of negative 7. Because it's a negative log, the negative of negative 7 is positive 7. And that's how I got my pH of 7. Using a Sharp calculator, you might have to type in 1 EXP plus or minus 7, and then hit the log key. It doesn't matter how you do it, you just got to know how your calculator works. We should all get the same answer, 7. Now, let's suppose that we make the solution more acidic. So we move it from pH 7 down to 6. And one might think that's not a big deal, right? Well, interestingly enough, if we dilute that acid by 10 times, concentrate that acid by 10 times, from 10 to the minus 7 up to minus 6, and we calculate the pH, we get the pH as a negative log of 1 times 10 to the minus 6, and we get 6. Now, you might be thinking, what's the big deal between a solution of pH 6 and 7? Well, there's a big deal there. In fact, the solution of pH 6 is 10 times more acidic than the solution of pH 7. So that is a really big difference if you're talking about the pH of a lake or a river or the body. The human body can only withstand very small changes in pH, to be honest. Maybe 0.1, to be honest. Very close. This graph shows us what I'm talking about. And it looks a little bit complicated, but it's not. At pH 7, over here, we can actually read the y-axis and get our concentration in moles per liter of 1 times 10 to the minus 7. We've already done that. If we make it more acidic, let's suppose we go from 7 to 5, so we change the pH by 2 units. If we go up and across, that concentration is 1 times 10 to the minus 5, which, if you think about it, is 10 times 10, or 100 times stronger than the solution of pH 7. Likewise, if I go to pH 4 and we calculate the pH of that solution, the negative log, then we end up getting 10 to the minus 4. That solution would be 10 times 10 times 10, or 1,000 times stronger than the solution of pH 7. So that's why pH is a logarithmic function, and there's a strong relationship between pH and H+. So bottom line, for every single drop in pH, so going from 7 to 6, 6 to 5, 5 to 4, etc., the acidity goes up by 10. If we go from a pH of 4 to 5, the acidity drops by a factor of 10. So it's a logarithmic function based on 10. And that's why we put the 10 there sometimes, although most textbooks don't do it in chemistry. So there is a quick look at the pH scale, the relationship between pH and H+. It is a logarithmic function, and it is a very good jumping off point for a few other calculations. Our next step is to focus a little bit more at this and figure out how to calculate the hydronium or H+ concentration from pH, going in reverse. Not a big deal. We'll also dabble in some basic solutions to figure out how to calculate something called pOH. It's really very similar to pH. The only difference is it applies to bases. And we'll look at the relationship between pH and pOH. Hopefully that helped. It's in section 10.2 in your text. The textbook does not do very much in terms of calculations, so I have beefed up this section a little bit. It becomes really important in the world of biology and grade 12 chemistry as well. Until next time, happy pH. Hopefully you can practice a little bit, use your calculator, and it should become quite easy for you.